Here's a wild thought. Every single solar panel on this planet is tested against a sun that, well, it doesn't actually exist. Sounds crazy, right? But today, we're diving into this standard sun. It's the universal yardstick that honestly makes the whole solar industry even possible. So let's get right into it.
All right, so let's just start with the core problem. Imagine you're making solar panels out in sunny Arizona, and let's say I'm your competitor over in cloudy Germany. How on earth can we figure out whose panel is actually better? I mean, your sun is not my sun. It's kind of like trying to have a fair race when the racetrack itself is shifting and changing under our feet. It's just impossible.
And that right there, that simple question, it really gets to the heart of the single biggest challenge the early solar industry had to solve. The sun is just, well, it's inconsistent.
You see, sunlight isn't this one uniform thing. The amount of energy hitting the ground, what scientists call solar irradiance, it changes dramatically depending on where you are. The sunlight you get in the tropics is totally different from the light in, say, North America. And it's all because of stuff like clouds, the time of day, the angle of the sun, even how much dust is floating around in the air. So yeah, trying to compare a panel tested in one place to another, it's pretty much impossible.
Okay, so when you have a problem this big, you need a pretty creative solution, right? If the real sun just refuses to play by the rules, well, then the scientific community had to do the next best thing. They had to invent a perfect one, a consistent one. And that was the beginning of the quest for a universal reference.
And the solution they came up with? It's called the AM1.5 standard spectrum. Now, the best way to think about it is like a super precise, universally agreed upon recipe for sunlight. It really is the gold standard that we use to test and compare every solar panel everywhere on the globe.
Now, this standard didn't just appear out of nowhere. It's been tweaked and refined for decades. I mean, look at this timeline. It all started way back in 1972. Then, in '82, it got a major update from the American Society for Testing in Materials. You'll hear them called ASTM. The version we all use today, that was locked in back in 2003. So you can see, it's really a living standard. It evolves as we learn more.
All right, so let's talk about that name, AM1.5. What does that actually mean? Let's break it down, and we'll start with the most important part, the AM. That stands for air mass.
So, air mass, it's really just a way to measure the journey sunlight has to take through our atmosphere to reach us. A simple way to think about it is that our atmosphere is like a filter. And the thicker that filter is, the more atmosphere the light has to punch through, the higher the air mass number.
Okay, let's really picture this journey. You've got AM0, that's sunlight out in space. It's passing through zero atmosphere, pure, unfiltered. Then you have AM1, that's the absolute shortest path possible, when the sun is directly over your head. And then we get to our standard, AM1.5. This represents the sun at an angle, so its light has to travel through 1.5 times more atmosphere than it does at AM1. See how that works?
But why 1.5, right? Why not 1 or 2 or something else? Well, it's actually pretty clever. AM 1.5 turns out to be a fantastic average for the solar conditions you find in the world's temperate latitudes. We're talking about places like the United States, most of Europe, and China, where most of us live and where, it turns out, most solar panels get installed.
Okay, so we've got the air mass part down. Now let's look at the other ingredients that go into making this perfect, standard, sunny day. It really is like following a very, very specific recipe. And when I say specific, I mean incredibly specific. This recipe for what's called the AM1.5 global spectrum defines everything. I'm talking about the tilt of the solar panel, the sun's power level, locked in at exactly 1,000 watts per square meter, and even the precise amounts of things like water vapor and ozone in the air. The big thing to get here is that this isn't just a photo of a real day. It's a carefully built model. It's a perfect, repeatable average.
So we've got the recipe, we've got all the ingredients, so what does the final cake look like? What is the official fingerprint of this standard sun?
Well, when you take all those ingredients, all those conditions, and you plot them on a graph, you get this. You get the official spectrum. It shows us exactly which colors of light actually make it down to Earth and which ones get filtered out by our atmosphere along the way.
And here it is. This graph tells such a cool story. See that smooth black line up top? That's the AM0 spectrum. That's pure, powerful sunlight, totally unfiltered, out in space. But then, look at that jagged blue line underneath. That's our AM1.5G standard. That's the sunlight that actually hits the ground. All those sharp dips and valleys, you can think of those as bite marks from our atmosphere. They're the specific colors of light that get absorbed on the way down.
And this whole filtering process is absolutely crucial. That chewed up spectrum, the blue line, that's the actual fuel that our solar panels have to run on. So understanding exactly which colors get absorbed and which ones make it through, that's the key to designing better, more efficient solar cells. You could say our atmosphere literally shapes the energy that we use to power our world.
Okay, so we've got this super technical, very specific standard. But so what? Why does it matter so much? Well, it turns out this standard isn't just some academic exercise. It is the bedrock of the entire global solar industry.
And really, the official document says it best. The whole point is to provide a single common reference for everyone to use when they're evaluating things. That's it. That's the core idea. One yardstick for the whole planet.
And having that shared benchmark, it's what lets the whole industry work. It means researchers can finally make fair apples-to-apples comparisons of new solar cell tech. It lets manufacturers guarantee the performance of their panels. It means engineers can accurately predict how much energy a huge solar farm is going to produce. It lets the whole global community innovate faster, together. I mean, it literally powers progress. So this all brings us to a final and pretty critical thought. This standard has already been updated in the past to account for things like rising CO2 levels. So that leaves us with a really important question. As our atmosphere continues to change, how is this artificial standard sun of ours going to have to evolve right along with it? What's the benchmark for solar power going to look like in, say, 50 years? It's definitely something to think about.